The shocking discoveries of the James Webb Space Telescope. Astronomers simply could not believe what they were seeing. There, in the infancy of the universe, were images of already mature structured galaxies, bright and contrasting, that should have taken billions of years to develop. It was like observing a centenarian tree sprouting soon after the planting of the seed. The standard cosmological model predicted a much slower and more gradual growth. But James Webb exposed a reality in a hurry. This initial shock came when astronomers used the James Webb Space Telescope, JWST, to peer farther back in time than ever before. According to the standard model of cosmology, galaxies were expected to grow gradually, starting as faint, small, irregular collections of stars and gas. They were not supposed to appear as fully formed spiral or elliptical systems so early after the Big Bang. Yet JWST revealed the contrary, mature galaxies that defied predictions. What was most surprising was the complexity of these galaxies. Many already featured second and third generation stars. And more astonishingly, heavy elements such as oxygen and iron were present in significant quantities. This means these stars lived and died quickly to enrich the interstellar environment so soon. This raises an obvious problem. Heavy elements, also called metals in astronomy, are forged in the cores of massive stars and then spread across galaxies when those stars explode as supernovae. If galaxies less than a billion years old were already enriched with oxygen and iron, it suggests that the first stars, the so-called population 3 stars, must have formed, burned, and exploded far faster than theories had anticipated. Even the boldest galactic formation models are challenged by this cosmic anticipation. As recent studies up to 2025 confirm, galaxies observed as early as 300 to 500 million years after the Big Bang are far more developed than expected. Scientists accustomed to working with extensive cosmic timelines now need to review their equations. The observations made with the James Webb Space Telescope indicate that the birth and growth of the first galaxies may have been much more efficient than any simulation suggested. Hypotheses propose extremely dense initial fluctuations as favorable conditions, but nothing conclusive has been established yet. These fluctuations would have created clumps of matter that rapidly condensed into stars and galaxies. However, simulations still fall short of reproducing the complexity of what JWST sees. This turnaround also sparks debates about the role of dark matter in this process. Could its initial distribution have helped shape these structures more quickly? Or perhaps there are still unknown physical phenomena interfering with the initial stages of cosmic expansion. Each new discovery defies prevailing logic, forcing science to seek answers in territories that once seemed too speculative. With ongoing research in 2025 exploring alternative models like modified gravity or early dark energy, cosmologists are beginning to ask whether fundamental assumptions about the universe itself need revision. As we try to decipher how these galaxies formed so far, so soon, the James Webb Space Telescope begins to reveal something even more intriguing. Structures even bigger, almost as if the universe was organized in patterns that defy chance. This is where we enter the domain of the impressive organized cosmic filaments. Imagine the universe as a colossal web where galaxies are not randomly distributed but connected by gigantic structures called cosmic filaments. In 2023, the James Webb Space Telescope revealed one of these structures composed of 10 galaxies aligned in a thread-like pattern dating back to only 830 million years after the Big Bang. This discovery offers an unprecedented view of the initial formation of the cosmic web. These filaments are not only vast in scale but also exhibit surprising organization. Studies indicate they can extend for hundreds of millions of light years with wave-like regularly spaced patterns resembling a cosmic architecture. This symmetry challenges previous predictions based on simulations, suggesting forces or processes not yet understood are shaping these structures. With recent 2025 analyses refining our understanding of their formation, the picture of a chaotic early universe is giving way to one that seems structured from the start. Beyond the James Webb Space Telescope, astronomers have identified about 1,978 galaxy groups, mapping the evolution of cosmic structures over 12 billion years. This sample, one of the largest ever observed, allows astronomers to study how galaxies form, grow, and interact over time, offering valuable insights into the large-scale evolution of the universe. The presence of these filaments and groups of interconnected galaxies suggests the universe has a complex underlying structure where matter is organized non-randomly. This organization influences cosmic processes from star formation to the dynamics of galaxy clusters. Understanding this cosmic web is essential to unraveling the mechanisms governing cosmic evolution. With ongoing surveys in 2025 providing richer datasets as we explore these vast structures, the James Webb Space Telescope continues to surprise by detecting gravitational anomalies in regions where there is no visible matter. These intriguing phenomena lead us to question what else might be hidden in the depths of the universe. In September 2023, the James Webb Space Telescope captured an impressive image of a distant galaxy identified as JWST ER1, surrounded by a near-perfect ring of light known as an Einstein ring. This ring was caused by the distortion of light from a galaxy positioned even further away due to the immense gravitational force of the intermediate galaxy. What surprised scientists was the mass involved, approximately 650 billion times the mass of our Sun, far higher than expected. After subtracting the visible matter, researchers found that a significant amount of dark matter, about 5 to 6 times more than anticipated, was needed to explain the gravitational effect. This result, confirmed in 2024 studies, raises the possibility that dark matter has properties still unknown, perhaps interacting in ways our current models cannot describe accurately. This was not an isolated case. The James Webb Space Telescope also identified gravitational distortions in various other regions of space without corresponding visible matter to explain these deviations. These anomalous patterns challenged the traditional model of dark matter distribution, which had assumed a relatively homogeneous dispersion of this invisible substance throughout the cosmos. These findings, corroborated by 2025 observations, suggest we understand very little about the true constituents of the universe. The telescope's unprecedented deep infrared observation capabilities allow it to see these subtleties with a level of detail never achieved, forcing the scientific community to re-evaluate the foundations of modern cosmology and seek new explanations for these mysterious forces. As we continue trying to understand these distortions of light and gravity, new observations reveal another intriguing phenomenon: rhythmic light pulses appearing in zones completely devoid of any visible source. A new enigma appears on the horizon. In early 2025, the James Webb Space Telescope captured an intriguing phenomenon. Pulses of light perfectly rhythmic with intervals of approximately 29.437 seconds emanating from regions of seemingly empty space. These signals persisted for 37 minutes before ceasing abruptly, defying conventional explanations. The absence of visible emission sources in these areas makes the phenomenon even more enigmatic. Astronomers have considered hypotheses such as neutron star pulsars emitting radiation at regular intervals. But the location in regions devoid of visible matter and the regularity of the pulses raise doubts about this explanation. Another theory suggests these could be manifestations of unknown physical processes, perhaps related to fluctuations in the fabric of space-time. As of 2025, no definitive explanation has emerged, and research continues. The precision of the intervals between pulses and their limited duration suggest a behavior that some consider intentional, though it is premature to assert any artificial origin. The regularity and abrupt cessation of the signals resemble communication patterns, a possibility that, while speculative, cannot be dismissed without further investigation. The James Webb Space Telescope, with its ability to observe the universe in infrared wavelengths, continues to reveal phenomena that challenge our current understanding. The detection of these light pulses in apparently empty regions highlights the importance of exploring the cosmos with new tools and perspectives. Each new observation may bring us closer to understanding the deepest mysteries of the universe. As we seek to understand these mysterious signals, theories propose that the universe may carry echoes of previous versions of itself, suggesting a gravitational memory or an eternal cycle of rebirth.